In this video, we will talk about how power can be obtained from work. In other words, how these two concepts are related. We shall look at the definition of power. In particular, there are two of them. One is the average power, and the second one is the instantaneous power. We shall look at how to calculate these two, followed by some solved problems based on the concepts that we have explained. Power is closely related to work, and the connecting factor is time t. Now, just like work is a scalar, power is also a scalar. It does not have any direction. More accurately, power is the time rate at which work is done by a force. An illustration of the concept of power is as follows. Now, let's say you have a weight that weighs 500 newtons, and you want to raise this weight vertically by a distance of, let's say, 2 meters. In other words, you want to lift this weight upward vertically by a distance of 2 meters. And you want to do that at a constant velocity without any acceleration. And you want to do this in, say, 10 seconds. So this is an example of how power comes into play. Well, how so? Now, since this weight weighs 500 newtons and you want to raise it vertically with a constant velocity, you have to exert the same amount of force in an upward direction as the weight. That means you have to exert 500 newtons on this weight in order to raise it vertically. And once you raise it vertically a distance of 2 meters, in 10 seconds, that means you have done a work to the amount of 500 times 2. So the amount of work that you have done is 1,000 joules. So this 1,000 joules of work is accomplished in a period of 10 seconds. So we say the rate of work done in this case is 1,000 over 10. So 1,000 is the joules and 10 is in seconds. So the power for this activity, the power generated by you, is 100 joules per second. Now, this joules per second can also be written as watts with an abbreviation W. So the SI unit for power can be joules per second or watts. Another illustration of the concept of power is, let's say, a truck towing a trailer. So that is the trailer. So the direction of motion is, of course, like that. So this car or this truck is towing this trailer. So the power due to the truck's applied force on the trailer is the rate at which the force is doing work on the trailer. Rate at which the force is doing work on the trailer. So you see the connection, the close connection between power and work, as power being the rate work is being done on a given object. Let's look at how to calculate power. Let's begin with average power. Now, if a certain amount of work W, so W is measured in the unit of joules, is done in a finite time interval delta t, so time is measured in seconds, then the average power is defined as the work done over that time interval. So here you can clearly see, since work is quantified in the unit of joules and time interval is quantified in the unit of seconds, power is computed in the unit of joules per second, or, as we explained a few minutes ago, watts. So the concept of average force is pretty simple. The work done over the finite time interval. And what about instantaneous power? Now, instantaneous power is defined as instantaneous rate of doing work. So as you can see, it is given in the form of derivative, time derivative of work done. And as always, it's pretty clear that the units is joules per second or watts. There is an alternative form for the power formula that we can derive in terms of force and speed, or velocity rather. So let's look at average power, PAV, and how we can obtain this alternative form for its expression. Now, since we have seen the average power is computed as work over some time interval, and we know from the definition of work that it is simply force times some displacement, say along the x direction, so over delta t. Now, the force, assume that the force is a constant force, so let's assume that this is a constant force. So if you take that out, the ratio will simply becomes delta x over delta t. And from motion, from our previous videos, we know that this corresponds to speed. So your final answer is average power can be computed as force times speed. So this is the additional or an alternative form depending on what information you are given in a particular problem. One can also do the same with instantaneous power. So instantaneous power P. Now remember the definition of instantaneous power. It is the time derivative of work. Now we know, again, work is, if you write the dot product form, dot product of force and displacement. Now let's assume that this is again a constant force. So you can take that out of the derivative sign. So it's going to be F dotted into dx dt. Now what is dx dt? Well, that's quite simply is the velocity. So you can write the following form as an alternative form for instantaneous power, for example, which is the dot product of force and velocity. Let's look at a problem. A man with mass 70 kg walks up to the second floor of a building. The vertical height is 15 meters above the ground floor. If he climbs the stairs in 20 seconds, calculate the rate at which the man is doing work, namely the power generated by him. So this diagram, this schematic diagram, depicts the situation. The person's weight is 70 times gravity. So this is the weight. And he takes 20 seconds. The time interval for him to accomplish this motion is 20 seconds. And he has to cover 15 meters vertically all the way from the ground floor to the top. So since his weight is 70 times gravity, he has to exert the same amount of force, at least, to go up vertically. So his force has got to be 70 times G in newtons as well. So how to compute the power? the average power. So in this case, the power, let's call it average, because on average is generating the same force as his weight, is given by the work done by him over the time interval. Now the work is given by the force that he exerts, so 70 times gravity, times the vertical height, which is 15 meters, over the time interval of 20 seconds. And that will give you, remember, G is 9.81, a value of 515 watts for the power generated by him. Problem 2. So here you have an 80 kg block pulled at a constant speed of 4 meters per second across the horizontal floor by a machine exerting a force of 100 newtons, directed at some angle 42 degrees with respect to the horizontal. Now, what is the average power of the machine's force on the block? Now, since we know that the speed is 4 meters per second, we can use the alternative form for power involving force and speed to calculate the average speed in this case. Of course, the origin of this equation is F dot V. So F is the force along the horizontal direction, let's call it the x direction, because velocity is already along the x direction. So we need to compute the x component of that force, and that is simply 100 cosine 42 degrees. So the component of this 100 newtons along the x, or the horizontal direction, and that we know it's the I hat dotted with 4 I hat, and that's going to be 400 cosine 42 degrees, which is 297 watts. And that completes the problem. Problem 3. A force of 8 newtons acts on a 16 kg body, initially at rest. So what is the instantaneous power due to the force at the end of the third second? So a force of 8 newtons is acting on it. Initially, it's at rest. So this is partly a kinematics problem. So the initial speed is 0 meters per second. Now we are interested in determining the instantaneous power at the end of the third second. So let's assume this is an instant when t equals to 0 seconds. Now t equals to 3 is when the object is, let's say, here. So of course we need to know what is the speed then. To determine that, we need to know the acceleration. So, well, do we know the acceleration? Well, acceleration from Newton's second law is given by the force, which is 8 newtons over the mass, 16 kg. Now this is quite simply F equals to ma. So to get the acceleration, you take the force divided by mass. And that will give you half meter per second squared. In order to get the speed at t equals to 3 seconds, you can use the first equation of kinematics, which is initial speed plus acceleration times the time interval. Since the initial speed is 0, the acceleration has been found to be half. Time interval from here to here is 3 seconds. So you see the speed of this object when it's here is 3/2 meter per second. So now the instantaneous power is quite simply the force that's acting on it, which is 8, times 3/2, which is 12 watts. So this is essentially the force dotted into velocity. The force is along the x direction. The velocity is also along the x direction. So F dot V is 8 times 3/2, which is 12 watts. And that solves the problem. Thank you for watching.